Hey, Alex, you're muted.
Thank you. Sorry about that. Hi, everyone. Welcome to our online training for Students Day presented by Global Software. Today, we'll be working with our FEA and design software, RFEM, and the goal of this training is to go over the fundamental knowledge needed so students like you can model and work with any type of basic structure, view results, and learn fundamental basic theories. And this training will mostly be focusing on simple models. So my name is Alex Bacon, and I will be your trainer for today. I am a technical support engineer, and I'm joined with my co-organizer, Amy Heilig, who is the CEO of the US office and a technical support and sales engineer. And we are located in Philadelphia, PA. So here's the control panel. This will be used throughout the training, and you can show or hide this panel as well as adjust audio settings. There's a box where you can find the materials for the training, actually, and there's also a chat box where you can ask questions as well. You can make sure that this is set to organizers only. And for this training, it's intended for you to just listen, but you can also model along if you would like. I can't stop and help you with any specific modeling issues, but with that said, feel free to stop and ask questions at any time. And Amy will answer the easier questions in the chat, and she'll save the more complex ones for before breaks, and we'll dedicate that time for more complex questions for me and her to answer. So for today, there will be 2 breaks. There will be one at 2 p.m. and also one at 3 p.m. and both of those will be 5 minutes each. And here's the content for today. So first we'll just start off with going through the principles of FEA, and then we'll go into an introduction into the RFEM software. And then we'll begin with our first example, which will be an introduction example using continuous plates. And with that one, we'll go through plate theory. And then after that, we'll do a stability analysis example called Eulero Case 1. And then we'll convert that example into a moment frame. And then the last example will be a timber truss girder. So with that said, we can jump into going over the basics of FEA. So when using computer software, it's based on the displacement method, and another method you may be aware of is the force method. And this is where the unknown is the force, and then the internal forces can be calculated based off of this. When it comes to the displacement method, the unknown displacement, and to solve for this, the displacement vectors must be calculated, and then the internal forces and support reactions can be figured out. And the main problem today is when it comes to analytical solutions, they can be difficult to determine when it comes to large complicated structures. So doing hand calculations for some structures with complicated and odd geometry can almost be impossible or feel impossible. And the limits are being reached with large complicated structures. So it's difficult to get accurate results. And this is where FEA software comes in. So structures are then modeled, complicated ones are then modeled and converted into a finite interconnected element mesh. And then the material and the cross-section properties are given at each FE node. And then the mechanical behavior is transferred between these elements. So here's a good word I would like you guys to walk away with and know is this discretization, which is when or how structures are being submeshed into finite elements, which is kind of the overall idea of FEA. So that's a good word to have in your vocabulary. Next, I want to go over the FEA calculation workflow. So this is also good to know for most FEA softwares. This is basically the workflow for them. So first, the local element stiffness properties are determined is the first step. And then those local stiffness properties are transferred to the global coordinate system. and then the assembly of the entire structure takes place. And the boundary conditions or supports are then defined, and these could consist of sliding, rigid, or hinged. And then the displacement vectors can be calculated by solving for the system of equations. And then lastly, the support forces and internal forces can be determined. So first question for today will be, what is discretization? And it should be pretty easy since I just went over it, but here are the options. So choose from A to C and just enter your answer in the chat, and we can see if the majority of everyone got it correct, and then we can go over it. All right, so it looks like a couple of you answered C, and the correct answer is A. So what is discretization? You could either choose from structures converted to finite elements, it's the calculation of structures according to the FEA, or C, submeshing finite elements into smaller elements. And the correct answer, like I said, is a structure being converted into finite elements. This is discretization, so that is the correct answer. Submeshing finite elements into smaller elements is not correct, and calculation of structures according to the FEA is not exactly correct either. So A is the correct answer. So next thing we can do is move on to our first example. So, and the first example for today will be the continuous plate example, and you can see a couple of continuous plates here in this picture. This is what we'll be modeling first in RFEM just to get started. And with this, we're going to compare moment results with the continuous beam. So this should be pretty interesting. So now what we can do is we can jump into RFEM. So here you can see RFEM is open on my screen. I just have this basic example open just so we can go through the user interface of RFEM. First, I just want to start off with the question, so what is RFM? So I'm sure you all can guess by now that it's FEA software, but to specify, it's structural analysis software capable of analyzing elements like plates, members, and solids. So then results like deformation, stresses, and internal forces can be calculated based on any 3D or 2D structures. And the great thing is almost anything is possible to analyze and calculate. And this includes things like volume and weight, so pretty helpful. So first we'll just go over the UI of this already modeled structure I have open. So on the left-hand side here, you'll see you have your project navigator with the name of your model, which I have opened already. And you can see this shows basically everything that your model consists of. So everything's organized in these expandable and collapsible folders. So elements like nodes, lines, and materials, you can easily get a quick glance at what everything is made of. So you can see this is concrete and steel. And then next we have our tables down here at the bottom. And these tables can act like your project navigator, basically going through and organizing all of your model data. But with the tables, you can change anything or add in model data. So if you wanted to model your whole entire structure with the tables, that is possible to do. So you can utilize that if you'd like, that workflow. Also, you can change the background color. So if we wanted to go up here into options and we wanted a black background, we could go to the configuration manager. And then you can see that we can change our background to black if we would like, and also some other options as well. I'm going to keep mine white. Then also we have the insert menu up here, which allows you, or which just organizes all of the tools. So if you wanted to insert nodes, lines, materials, members, this is all organized up here in this tool table here, drop-down window. So that's helpful if you don't want to use the tools up in your toolbar, which is the next thing to go over. So here is all of your tools, basic tools that you need to go through and model your model. If your toolbar doesn't look like this, you can rearrange your tools, but also if you just like that done automatically, you can right click anywhere in this gray space and hit reset to default, and then that'll reset your toolbar to look like mine. I think this is the best layout. Everything's organized where it should be, and I think it's helpful. So then we can also change the view of our model. So we can use these buttons here to view in the X direction, the Y direction, or the Z direction. There's also additional options for reverse directions as well. And then you can also hit this button to set it back to isometric view. In the project navigator, if you scroll down, you have a folder for your add-on modules, and RFEM is great for checking and analyzing basic results such as deformations, internal forces, and support reactions. But if you want to get into designing specific materials such as steel and concrete and timber, this is where, according to a standard, or this is where you would like to choose an add-on module to do that. So we'll go over those more in depth later on, but next tab we have down here in our project navigator is the display tab, and this allows you just to turn off aspects in the graphical window. So if you wanted to turn off something like surfaces for some reason, this just turns off the display. It doesn't actually get rid of the surface. So these surfaces are still there, just not displayed. So you can turn things on and off in here. You can manipulate results and things. So we'll go over this also more in detail later. And then we have our views tab. So here we can set visibilities, and we can view things based on members by cross section. So if I only wanted to view my W18 by 50 cross sections in my model, I could do that, and you can see it grays out the whole rest of the model here, and I can easily point out my certain cross section there. And then the fourth tab, which you can't see right now, is the results tab. So if I go up here and hit show results, and I turn off my visibilities, so now we have the fourth tab here, results tab, and this is how we can choose which results we would like to show on our model. So right now I could show just my global deformations, and now you can see the global deformations graphically as well. So we'll go over how to view results and how to use this efficiently within the upcoming examples. Last thing to go over is just movement. So if you have a mouse with a scroll wheel, you can press in the scroll wheel and you can move in your model in translation. You can also use the scroll wheel to zoom in and out. And then if you hold Control and press in the scroll wheel, you can rotate your model. So those are the basic movements. If you don't have a mouse and you're using a trackpad, you can use the keyboard arrow keys to move around. You can also hold Control and use the arrow keys to rotate. And then you can hit the plus and minus buttons to zoom in and out. So before we get into the continuous plate example, I just would like to pose one question. what is RFEM? So if everyone wants to answer or put their answer again in the chat, then we can go over the correct answer in a minute. Okay, great. So it looks like a lot of people answered. So what is RFEM? A, 3D structural frame analysis program. B, 3D FEA program for calculating members, plates, and shells. Or C, 3D FEA program for calculating members. A is incorrect because RFM can do more than just frame analysis. C is also incorrect because yeah, RFM can calculate more than just members. So B is the correct answer. 3D FEA program for calculating members, plates, and shells. So things like surfaces and solids can also be calculated with an RFM, and it's an FEA finite element analysis program. So great, looks like most of you got that correct. So yeah, now we can move on to our example. All right, so the first thing we want to do is create a new model. So we can go up here in the upper left-hand corner and hit new model. So the model name will be the first thing we want to enter. So we'll name it continuous plate. And I have multiple ones of these saved, so I'm just going to add a 20 after that, not to overwrite any of my other examples. So yeah, model name, and then description. This is optional, you don't have to add a description, so we can keep that blank. Then the project manager you can use to manage your project, so you can create local folders saved to your computer, and then you can manage these and set a project to that folder. So then if you have multiple models for a project, you can just have this easily save automatically to that folder. So then type of model, this one is going to be a 3D model. And then the classification of load cases and combinations. So you can have your load cases and combinations generated automatically according to a standard. So if I hit this dropdown, you can see we have most standards here to choose from. For today, I'm just going to use the ASC 716 just for this example, but we could have used any other standard as well. Check off this box to have the combinations created automatically. And then down here, you can set the orientation of your global z-axes. So there are two axis systems, the global axis system and then the local axis system. So if I click on this details button here, you can see that each element in RFEM has a local axis system, and we want to have this set to downward. So now that all of these options are chosen, we can, in our general data, we can click OK. And one other thing I'd like to also mention is I'll be using imperial units for this example, but you can change between imperial units and metric units pretty easily by going up here to options and then units and decimal places. So if I wanted to switch from imperial units, I could have open this up, and then there's a button down here called Load Safe Profile. So RFEM comes with 2 load safe profiles by default, metric and imperial. And if I wanted to switch to metric, I would just have to double click on it. Or if I wanted to set metric to my default, I would check off this box here. So for now, for this example, I'll be sticking with imperial, but just know that you can switch back and forth between those pretty easily. So now you can see we have our blank work window here. You can see we have our grid, which for imperial is 50 feet by 50 feet. And each one of these grid points is a foot spaced. And you can go up here to the settings of work plan / grid to change any of these parameters. So you can see here under grid point spacing, the base and height is 1 foot. And then in each direction, there's 50 grid points. So my grid is 50 by 50 up in the second quadrant here. So now what we can do, the first thing we want to do is just create one of our plates. And to do that, there is this tool here called New Rectangular Surface. So if I click on that, you can see this dialog box will pop up called New Rectangular Surface. And the first thing we want to do is create our material. So you can see here, I already have a material loaded in, but if you don't have this loaded in, you would want to create a new material. You can see here, you can create your own custom material by just entering the material constants, or we can choose a material from the material library that RFEM has built in. So I'll choose that. And then this material library dialog box will pop up. And on the left-hand side, you can filter to concrete. So for this example, we'll be using concrete. And then the material category. And then for this example, I'm going to use the ACI standard, but you can also choose from other standards to pick your material out. You can see we have the Canadian standard as well as Eurocode. So I'll choose ACI, and then I'll choose the 2019, the latest standard, and I want this to be 4,000 PSI concrete. Then at the bottom here, you can also see your material constants or material properties. If you would like to check those, you can do that. So I'll just hit OK. And now the next thing we need to tell the program is what the thickness of this plate is going to be. And for this example, we're going to make it 12 inches. And now everything else is basically entered, so we can click OK. And you can see my cursor has turned into this reticle here, so I can snap to any of these grid points to put down the first corner. And the first corner is going to be located at the origin. So I'll left click on the origin, and then this plate's going to be 32 feet by 16 feet. So I'll go 32 and then up here to 16. And then I'll click again. And now you can see our first plate has been created. Now the next thing we can do is we can either just draw the same plate up at the top here, or we can use the move and copy tool. So what I'm going to do is just right click to cancel out of that tool. And then I'm going to just highlight the whole plate here. And I can hold my control key down and then left click, and I can move this plate up, and I'm going to have these 2 plates spaced out by 5 feet. And then the other option you can use is the actual move and copy tool. So if I highlight the second plate here, and then I go up here to this button here called, or tool called move and/or copy. I can click on that, and then I can make one copy of this plate, and I want to move it in the in the Y direction, 21 feet. And then I'll click OK. And now you can see that I created a second copy of the plate and 21 feet. The reason for that is because I wanted to have be spaced 5 feet from this plate here. So now you can see we have all three of our plates, and there is a couple ways of modeling your plates or modeling a copy of something. Then just to clean up the model a little bit, I'm going to highlight all three of these, and I'm going to just drag this bottom left-hand corner of the second plate down to the origin, just to keep our plates within our grid here. And then also I just want to make some space for the beam that we're about to model at the top. So to create a continuous beam, we're going to go up here to new single member. And in this new member dialog box, looks a little similar to the one for surfaces, but it's a little more complex, as you can see. So what we want to do is tell the program basically what cross-section and material this member is going to be. And you can see there's a member start and end. Just focus on the member start. So the whole entire member will be this cross-section of material. We can click on this button here, create new cross-section. And then you can see you can enter manually the cross-section properties, just like the surface, or you can go up here to this button, import cross-section from library, which is what we want to do. So we'll click on that. And then you can see we have our categories here in the material or the cross-section library. So we have our rolled cross-sections based on standard or standardized rolled cross-sections. And then we have our built-up sections here. And then we have our parametric thin-walled sections. So you can change these dimensions or input them manually as you would like. Then we have parametric massive, which is what we're going to use for our concrete continuous beam. And then parametric timber, and we have then standardized timber down here. So I'll just choose the rectangular section from our parametric massive category. And the base of this is going to be 40 inches. And then the height is going to be 16 inches, or 12 inches. So similar or exactly the same as the thickness of our plates. And then the material we'll be using is the same as our plates, so 4,000 PSI concrete. So I'll click OK and click OK through all of these dialog boxes. And then I can start drawing my beam. And I'm going to make this 5 feet away from the plate, like the other plates. So I'll just click for the member start. And then I'll click for the member end. And I'll right click to cancel out. And now you can see we have our continuous beam here. So now the next thing we want to do is we need to divide these lines here because we're going to add in some center supports to the midspan of our plates here. So there's multiple ways of dividing lines with an RFEM. So I can just right click on this line here, and then my shortcuts menu will pop up, and I want to go to divide line, and you can see there's 3 options for dividing a line. I can divide it graphically, which just allows me to snap to a grid point, and I want to divide it directly in the middle at 16 feet. And I could just keep going to the next lines to divide them. But there's also a couple other options, so I can divide them by an intermediate node. So you can see here I can divide line by an intermediate node, and this will just divide it evenly. So if I just choose one node, It'll put a node directly in the center of that line. And then the third option is you can do it by distance. So if you really want to get accurate on where this node is going to be, you can see here, I can either do it 16 feet from the start or 16 feet from the end or 50%, so it's in the middle. And basically I can just hit OK. And now it's going to put that node right in the middle. And if you're ever confused about the direction you drew your lines, you can see when you hover over them, there's an arrow here telling you which way you drew your line. So this is helpful mostly for members, but also for lines if you're dividing them and not sure where the member start or end is. So then I'll just do the rest of these graphically. So I'm just going to place some nodes here, right in the middle. And then I'm going to divide my member here, just using n intermediate nodes. So we'll click OK. And now you can see my beam here is divided into two sections. So now we can create now we can add our supports. Actually, before we do that, we need to add in lines to connect these nodes. And to just draw a line, you can go up here to this tool called New Line. And then we can snap to our nodes that we placed here. And we can simply just go through and draw our lines. Just like so. And now we can add our supports in. So to create a new support, we can go up here to the new line support. So we're going to support this center span continuously along this line. So we want to use a line support. And this line support is going to be hinged. So then nothing can move in translation, but all of the degrees of freedom for rotation are released. So you can see we have templates, or we have our already defined supports, but if you wanted to create your own custom definition, you can create a new support here. And then you can see you can check or uncheck one of the degrees of freedom. So all three of these are in translation, and then we have rotation. So for a hinge support, we would just check and fix all of our translation directions here, and then we would uncheck and release all of our rotation degrees there. So we'll click OK, click OK again, and now we can just simply select all three of our lines here. And this is going to actually be the same for our outside. Surface is right there. And now we just need to support our beam here. And this is going to be supported using nodal supports. So I'm going to go up here to new nodal support. And two of these end conditions are going to be hinged. So we'll make the end here hinged and the middle hinged. But what we need to do is fix the rotation about the beam's axis here. So if I right click, we can show the local axis system of this beam. And that'll show the local axis system of all of the lines there. So actually turn that off. So here's the local axis system of the member here. And what we need to do is if we put a third hinge support here, then the member would be able to infinitely rotate about its x-axis here, and that would cause a instability in the program. So what we want to do is go up here and click on new nodal support. And what we want to do is create a new type of nodal support. And we want to fix the rotation about the x-axis, keeping the member from rotating about it infinitely in the program. So now you can see the difference between the support with the fixed X rotation and these two hinge supports that have it released. So now that we have all of our plates here and our beam here fixed, we can now get into loading. So before we can add in any loading, it's important that we create a load case because every load needs to be assigned to a load case within the program. So what we want to do is go up here to this button, new load case, and this will open up our edit load case and load cases and combinations dialog box, and you can see a load case has already been created. So now what we want to do is give this load case a description. So this will be test, and then the action category according to the ASC 7 is dead. This is fine. We don't really need to worry about action categories or anything for this model. We're just going to use this load case to add in our loading. So, and we also want to, you can see self-weight for the dead load action category is automatically checked. So this will take self-weight into account for your model. So what we want to do is uncheck that for this example, and we'll click OK. And now you can see we have our load, we're looking at our load case here test. So any loading we add right now will be added underneath this test load case. So now we want to do is create some surface loads to apply to our plates here. So we're going to go up here to the tool called new surface load. And this is the new surface load dialog box, and we want it to be a force. So you can see there's multiple different load types here. Load distributions, we want it to be uniform, and then we want it to act in the global Z direction for our load direction. So it'll be acting downwards. And now we just need to specify a magnitude. So this magnitude, we need to add a negative sign, and it's going to be 210 pounds per square foot. So that'll be 0.21 KSF. And then we can click OK. And now we can just select our surfaces here and apply that loading to our surfaces. Now we can't apply that to our beam here because this is a member and not a surface. So what we want to do is add in a member load. So there's two options, a line load and a member load. Member loads are for members, line loads are for lines, so keep that in mind. We'll open up the member load tool. And this is similar to the surface load. So we're going to have a load type force, and then load distribution will be uniform. And the load direction is going to be in the global Z direction. And then our magnitude is going to be the same as the plate. So negative 0.210 kip per feet. So we'll click OK. And now we can apply that to our beam. And we can right click to cancel out. And now you can see we have our uniform load applied to our beam. Next thing we want to do is, for example purposes, we want to create some FE mesh refinements. So for now, I'm just going to unshow the loading on our model just to get a better look. And to add in FE mesh refinements, we can simply just right click on one of our surfaces. And there's an option here called FE mesh refinement. And we want to go to new. And now we just need to create a new FE mesh refinement definition. And what this does is it just allows us to specify a FE length for for a specific surface. So for this plate, we want the element length to be 0.2. So we'll click OK and click OK again. And then you'll see this symbol here applied to the surface, saying that there's an FE mesh refinement here. So the whole entire surface will have a FE mesh length of 0.2 feet. And then we're going to do kind of the same thing for this next surface. We'll right click on it, go to FE mesh refinement, and then go to new. And you can see that definition I made earlier of 0.2 feet was saved, but we want to create a new definition again. And this one is going to be 0.04 feet. And then we're going to do the exact same thing for the third one. We can also go to the project navigator, and you can see now the FE mesh refinements folder has a plus sign next to it saying that we have some FE mesh refinements in our model. What we could do is just right click on this folder and then click on new FE mesh refinement. And this third one is going to be 0.6 feet. So you might be catching on to the reason of doing this. I gotta specify the surface up here so we can do that graphically. So I'll select that surface. And what this is going to do is allow us to see the difference in results depending on the size of your FE mesh. So that'll be interesting once we run our results. Next thing we want to do is create some section cuts for our plates here. So this will also just allow us to be able to view the results of the section cut right through our plate. So to create a section cut, we can go up here to define section and results diagram, and we can go to create section numerically. And then the section name, I'm just going to name this one AA, and we need to choose where the point A and point B of our cut will be. And we can use this button here, select edge points of the section. So I can snap to the center point of this line here, and then snap to the center point of this other side. So this will be point B. And that's basically everything you need to set. So you can see the plane that this section cut will be in is the local positive z-axis, so it'll be pointing upwards, and we can click OK. So now you can see we have our section cut, and you'll see how this helps us view our results once we run them. Then we want to add this section cut to these other two surfaces, and an easy way to do that would just be to hit Control and then left click, and then we can just drag that section cut over like so. You can snap to that center point again, select it again, hold Control, and then left click. And now we have section cuts on all three of our plates. And you can see the names are a little awkward. So what we can do is go over here to the project navigator and then go to our folders and look for sections. We can expand that and double click on our section cuts here and just easily edit the name real quick. You can do that for the last one. Click OK. And now we have our section cuts. And then now we're all ready to run our calculation. So we can either just hit show results to see the results for our LC1 here. But if we wanted to run the results for all of our load cases and combinations and everything, we can just go over here to this button called calculate all. And what this will do is just run through the calculations, and it should be ready pretty quickly for this model. So now you can see we have our global deformations now shown on our plates and also our beam here. Right now it's just a yellow line showing the deformations for the beam. And then you can see now we're in our results tab. on our project navigator. So this is where we can choose what results we want to show. So right now I have global deformations checked, and that's the resultant. You can also take a look at the components and the X and Y and Z directions as well. Right now we're getting a max deformation of 0.02 inches, so pretty minimal. And the next thing we can look at is, for example, the internal forces of our beam here. So we'll check on that. And right now we're looking at our bending moments about the y-axis, local y-axis. So you can see that moment diagram displayed on our beam here. I can change the rendering of our model from a solid transparent display to a wireframe view. So you can see that basically members in RFEM are just 1D member elements. So the rendering makes it look like they're 2D elements, but really they're just 1D elements in the background. But now you can get a better look at that bending moment diagram. So we're getting a max bending moment of negative 6.7 kip feet there. Then we can also take a look at our internal forces on our plates. So if we scroll down here to check on surfaces, right now we're looking at our bending moments along the local x-axis. So every element, like I said, has a local x-axis, and this is what the lowercase x means. If you see a lowercase letter next to the symbol, that's telling you that it's using the local axes of the plate. So if I right click on my surface, which is easier if I change this to a different, there we go. I can go to the local axis system, and now you can see what that looks like on our plates. And so in order to see the results better, I can also activate those on our plates. I can activate my section cuts. So if I scroll down here in the results tab, still in the results tab, everything's just expanded. But you can see we have sections now, and I can activate those. And now you can see the results for our moments better, just with moment diagrams, basically through that section cut on our plates here. And maybe now you can also see the difference in accuracy between our plates here, depending on the FE mesh size we chose. So this first one was 0.2, and then we increased the length between all of them. So that's showing you how the results and accuracy can change. So also now's a good time to mention the size you pick for your FE mesh does affect your results. So if we go up here to calculate and go to FE mesh settings, this option here in the first general one, target length of finite elements, this is your global FE mesh. So if we didn't add refinements to these plates here, then 1 foot would have been the mesh size, which would have probably been a little too big for these plates, but you can see how the results can change depending on the mesh size you choose. Next thing I want to show you is if we go again to calculate, and then we go to calculate parameters, calculation parameters. Another thing I want to get into, or next topic, is shear stiffness. And first I want to show you how you can, with this option, deactivate the shear stiffness of your members. So right now, by default in the program, shear stiffness is activated for members, but if I uncheck this, then it won't be. And this is important because if you're trying to compare hand calculations to RFEM, RFEM is always running the calculations with shear stiffness considered. So once I uncheck this and I click OK, it's gonna tell me that I'm gonna need to rerun my results because this option is going to change the results. So I'm gonna click no real quick just to show you, but right now our max bending moment is 6 kip feet, so 6.701, so we'll just see that it shouldn't change too much, but if I hit OK and delete the results, and then I just quickly rerun them, you'll see, or you should see, some change in results a little bit. So we were at 6.701, and now we increased our bending moment a little bit to 6.72. So nothing too large in change, but this is important to keep in mind if you're comparing hand calcs. And the reason that this change happens is because the methods mostly used in school assume that each member has an infinite shear stiffness when in reality there is some shear deformations happening when members or beams bend. So it's important to keep this in mind again when comparing hand calcs. So based on shear stiffness, I just want to go back to the PowerPoint, and we can start talking about plate theory. And this will make more sense once we get into it. So I'm going to switch back to the PowerPoint. So to help understand plate theory, or how to help understand it, I'm going to use beam element theories as an analogy. So the first beam element theory is Bernoulli's, and then the second one is the Timoshenko theory. So with Bernoulli's, two major assumptions. The first one is that the cross-section always remains in plane and is perpendicular to the member axes. And the second one, most importantly, is that there's no consideration of shear deformations and the shear stiffness is completely rigid. For the Timoshenko theory, the first assumption is the same as Bernoulli's, that the cross-section remains in plane and that it's always perpendicular to the member axes. But the biggest difference is that shear deformations are taken into consideration and the shear stiffness is limited and not completely rigid. So you can see here that the deformation for Bernoulli's looks something like this and is perpendicular to the member axes. Whereas with the Timoshenko theory, we have an additional angle here. So this is going to lead to additional deformations, and this is due to that shear deformations, taking that into account, that the shear stiffness is not completely rigid and changes. So now knowing these two theories, we can use this to apply the same idea to our plate elements, or to plate theory. So a similar theory to Bernoulli's theory for plate theory is Kirchhoff's theory, and then for similar to the Timoshenko theory is the Resner-Millin theory, and this kind of works the same for plates. So the assumptions for the Kirchhoff theory, here they are listed. So basically we're assuming small deformations and that they are linear deformations. Also, we're assuming that the material used is linear elastic, so using Hooke's law. We're also assuming that the cross sections remain flat with no warping, and that the plate has constant thickness. And then the major assumption is that there is no consideration of shear deformations. Now, for the Resner-Millin theory, we're assuming all of the same assumptions, and as you may have guessed by now, is that for this theory, that the shear deformations are considered, and also for this one that we're taking into consideration transverse/lateral strains. And what I mean by transverse slash lateral strains is if we look at this diagram here, you can see we have a beam, and with this beam, we have tension forces. So we have a force on each side, putting the beam into tension. And when this tension force is applied to the beam along its length, the cross section will shrink with regards to its height and width. And you can see that that height and width shrinkage is based on this mu factor here, and this is how that is taken into consideration. So again, we have our two plate theories, the Kirchhoff theory and the Resner-Midland theory. And again, just to summarize, the Kirchhoff theory is great, has great results when using thin plates. For example, concrete slabs work great. Again, no consideration of shear deformations, and keep in mind that this theory only considers a pure bending loading bearing capacity. So this again is just more of a simplified approach. So keep that in mind when using the Kirchhoff theory. And for the Resner-Midland theory, this works really well for thick and thin plates. And in my opinion, the Resner-Midland theory is what you should use most of the time, but I just think it's good to know the difference between these two. So again, just to keep in mind that you'll get more accurate shear forces since the shear deformations are taken into account for this theory, and these other things like significant error when neglecting shear force, and it's going to yield a higher value approach when using this theory because of the additional deformations leading to additional shear forces or from additional shear forces. So these are two good theories to keep in mind. And now we can switch back to RFEM and see how we can apply these theories to our actual model. So now we have our plates here, and if we go up here to calculate and we go to calculation parameters, you will see under calculation parameters that we have our plate bending theories down here. So by default, RFM uses the Resner-Midland theories, which, like I said, works great for both thin and thick plates and just produces more accurate results. So if you wanted to use the Kirchhoff theory, you can switch to that. So if we switch to that right now, you can hopefully see these results. So about 6.592, we'll just keep an eye on this one, 6.594. So if we change this and we click OK, it's going to ask us to recalculate. And if we run this calculation real quick again, then we should see that our bending moments will increase from the decreased deformation. So yep, so 6.6. It was about 6.59. So not much change in results, but still just increased accurate results there with the Resner-Midland theory. So now I'll hop back to the PowerPoint to pose a question. And here is the first question. Which of the following is always true when considering shear stiffness? So again, if you guys want to answer that, and then we can go over them. All right, so it looks like we have some mixed answers. So again, the question was, which of the following is always true when considering shear stiffness? And the first option is shear deformations are considered. And the second option is increased accuracy in results. And then the third option is the shear stiffness of elements is infinitely rigid. This is a little bit of a tricky question, but the correct answer is A. So when considering shear stiffness, shear deformations are always considered. That's the correct answer. B, increased accuracy in results. This is not true for all plates. So for thin plates, accuracy in results isn't really true because then the results don't really change much for thin plates. So mostly for thicker plates, the results will change and the accuracy will be increased. And then for C, the shear stiffness of elements is infinitely rigid. This is not true because when shear stiffness is considered, the stiffness of the element isn't infinitely rigid. So that is that question. And so it's also around 2 o'clock. So if there's any questions, Amy, that we can go over before the break, we can answer those now.
Yeah, I think one question that was asked is how to import in a CAD file. So let's say from AutoCAD, how can this be addressed in RFEM?
Yeah, so AutoCAD is great for importing and exporting between RFM and AutoCAD. So if I hop back to RFM, we have some up here in this toolbar, we have some direct import options. So you can directly import from AutoCAD and directly export to AutoCAD. You can use some similar file types. So if we go to import, if we're importing from AutoCAD, there are some similar file types you can save your file as when importing and going back and forth between AutoCAD and RFM. But the important things to keep in mind is that really only nodes and lines can be imported from AutoCAD. Surfaces, you have to define them as I can't remember the name for them in AutoCAD, but they have to be specific surfaces. You need to create an AutoCAD for them to be imported into RFM.
3D
You can,
faces.
yeah, thank you. Yeah, 3D faces, those have to be defined in AutoCAD if you want surfaces to be imported from there. But you can define, you can have members and cross sections of materials imported from AutoCAD with those lines. So you can define those in AutoCAD and have those automatically imported. And so basically you can have um, members and cross sections of materials and everything imported, but when it comes to surfaces, it's not as straightforward.
Yeah, I think that's fine. And the additional thing to remember is that you can also import a DXF as a background layer. So if you'd prefer just to use the background layer for snap points and to draw your model in RFM, that's also possible.
Mm-hmm.
Um, so I think that that will go ahead and address that question. The only other question that maybe I'll just reiterate is the topic of setting the local z-axis down. It was asked, maybe why we need to do this. So Alex, I think you can answer that with the local axes.
Yeah. So yeah, for that local axes, I mean, you can have it set to upward, but we always recommend setting it to downward just because this is kind of how some of our add-on modules work. For example, the concrete add-on module, this is mostly designed and based on having the local z-axis set to downward. And when you set it to upward for some modules like the concrete module, your results could look inaccurate. So having this set to downward is important.
Yeah, and I also had mentioned in the questions dialog box that this will be addressed in a future version of RFEM where this will no longer be an issue, that you'll be able to use either the local axis Z up or down. A few more questions that came in. Does RFEM produce shop drawings? And the answer to that is no. So it is purely for the structural analysis only. It does not produce any drawings meant for fabricators. Are we going to upload this training presentation to YouTube or somewhere else? We will upload it and make it available to download once we have wrapped up this presentation, and it should be also available, I believe, on YouTube. I can't remember our exact process, but regardless, one way or the other, we will send you an email afterwards, usually within the next day, so probably tomorrow, with the access to this recorded training. The final question that we have coming in before this break is, how does the analysis of the diaphragm for seismic consideration, or how to do the analysis of the diaphragm for seismic consideration? We do not have diaphragms in the program. This is something that we're working on for a future release for more building type features. So we'll have rigid, semi-rigid, and flexible diaphragms, but this is not incorporated into RFEM now. Of course, you can draw a surface with the relevant materials and properties for a semi-rigid diaphragm, but it's not an actual diaphragm element in the program. It's really just a surface or a plate element, and we don't provide the analysis with cords and collectors and things like that at this point. So it's just purely FEA. So hopefully that answers that question too. Okay, I think that that's it for now.
All right, thanks, Amy. Yeah, we can now take a break. So yeah, so everyone, we'll just meet back here at 2:13. So we'll take a quick 5-minute break, and yeah. All right, so let's jump back into it. I actually have one more question to ask everyone, or this is a true or false statement before we move on to the next example. So the statement is the Kirchhoff plate theory does not consider shear deformation, and then you can answer either true or false. All right, so looks like a couple of you answered. So the correct answer is true. So the Kirchhoff plate theory does not consider shear deformations. So that is true. And we can now move on into our next example. So that will be the Euler case 1 example. So with this, we can hop back into RFM. And now for this example, we'll be creating a new model. So we'll go up here to new model, and the name of this will be Euler case 1. And everything else will stay the same. It's going to be a 3D model. We'll just keep our load cases and combinations created automatically. Everything is set, so we'll hit OK. So now again, we have our blank grid here. And the first thing we want to do is create a new cross section. So we can go up here to new single member. And this new member, so we'll create a new member and we'll use the cross section library. So this is going to be a W shape. And we'll filter to the AISC and the manufacturer, and then we'll choose W shape. And then this is going to be a W shape 12 by 35. So we'll scroll down here to 12 by 35. We don't want it made out of concrete, so we can go to import material from material library. And it'll be metal, steel, and we'll use the ASTM for this example. And we'll just make it steel A992. And click OK, and then click OK again, and click OK one more time. And so this is going to be a 30-foot tall column. And we basically want to draw this member perpendicular to our plane here. So a couple options for that. We can either choose the option in this tool here, length and direction, and we could just type in 30 feet and select the option perpendicularly to work plane in the positive direction. Now you can see I can just draw this. I can select the origin here, and the program will just draw that member 30 feet perpendicular to our grid here. The other option would have been to change our work plane. So we can do that up here with these three options. right now the work plane is in the XY plane, but we can easily just change it to we could have drawn our member up the plane there, and you can see again it's 30 feet tall. So we'll just change our grid back to the XY plane. And then next thing we want to do is support this column. So we'll just highlight from left to right to only select the node down here at the bottom. And then we can go up here to new nodal support. And we want this nodal support to be a completely rigid support. So you can see all 6 degrees of freedom are fixed. So we'll click OK. And now we have our column framing into the support. And basically this is our model. So what we want to do now is create a new load case. So we'll go up here to new load case and we'll name it test, just like we did in the previous model. And we'll turn off self-weight. So we'll deactivate that. And then we can click OK. And now what we want to do is add in some nodal loads to our column here. So we can drag from left to right to select our node up here at the top. And then we want to choose the tool new nodal load. And then the force will be we'll make it 5 kips in the Z direction, so -5, so it's a gravity load. And then we'll add just a lateral load in the X direction of 2 kips. So once we do that, we'll click OK. And now you can see those loads are added to the top of our column here. And next thing I want to do is show you something very important. So I'll hit calculate. And then we can take a look at our deformations. And if we look at this column from our side view, you can see it's deforming in the Y direction. And if we go to display, and then we choose under results, under deformations, and under members, we can choose colored sections, or cross sections colored. And now you can see the cross section here that's deformed, and we're getting a max deformation of 3.78 inches. And then we can also take a look at our internal forces. So I'll check on members. And then under internal forces here, I can show the bending moment about the y-axis. So you can see at the bottom here is where we're getting our max bending moment of -60 kip feet. And with that shown, we can, so we're getting a max moment of 60 kip feet at the bottom and a max deformation in the X direction of 3.782 inches. So keep that in mind. And now I want to show you how this linear or first order calculation differs from a second order calculation. So what I'm going to do is open up the load cases and combinations box. And by default, all load cases are calculated based on a first order analysis. So this is our load case here. And if we go under calculation parameters, you can see we have a couple options for the method of analysis. And like I said, by default, load cases are calculated according to a geometrically linear analysis, whereas load combinations, which combine load cases into bigger combinations basically, are calculated based on a second order analysis, which takes little and big p delta into account. And what we can do is change our load case to a second order analysis. And basically the difference at first order analysis sets the equal of the beam based on the undeformed system or undeformed beam, and a second order analysis sets the equilibrium based on the deformed system. So what I can do is show you how these results and deformations change based on the results or based on changing this to a second order analysis. So you should see that the deformations and bending moment will increase, and this is because of the P delta effect. So now you can see that we're getting a deformation or max deformation of 3.9 inches, which will in turn increase our bending moment or max bending moment to 61.6 kip feet, based mostly because of that increased moment arm. So we'll get an increased moment. So keep this in mind when you are looking at load cases and load combinations, where the results can change depending on whether a first order or second order analysis is ran. Another quick note is that members in RFEM are determined to be either a beam or column based on how the loads are applied. So in this case, we have a column here, mostly because of the axial force applied to it. So even though if we double click on this member, even though the member type is set to beam, this is the member type you want to use whether you're modeling a beam or a column. It all just depends on the internal forces within the member. So I'm going to, for the next topic, I'm going to change the loads here at the top to only be in the axial direction. And so we'll change the axial load to 0.1 kips, so 100 pounds. And then we're just going to change our lateral load here to 0. And once I do that, I'll click OK. And I actually need to switch the direction. So I'm going to double click on this load and change the sign of this. So it's a gravity load. And next thing we're going to do is get into one of the add-on modules, and that is the RF stability add-on module. And all students have access to all modules, so you should have access to the RF stability module. And what this does is help with the help of eigenvalues and different eigenforms, we perform a stability analysis on this column. So to access that, we can either scroll down here to the add-on modules folder, and we can look for our stability. I have it saved up here in my favorites folder, or you can also go up here to add-on modules, and then we can go to stability, and then RF stability. And then you'll see the RF stability add-on module open up, which is basically just a dialog box within RFEM. And just some quick background on stability analysis. So Euler was a mathematician who came up with different cases to show the critical loads, as well as or critical load factors, as well as critical loads and lengths. And so this is something that every stability analysis does, and it's important to, when you're using this module, it's important to activate the division of straight members. So you can see that's activated by default already. You can edit the options for this. So if we go to edit FE mesh settings, we can then go down here to the minimum number of member divisions, and we can change this from 2 to 10. And what this does is just increase the accuracy of your results. So we'll click OK. And then that's basically everything we need to change. So we're running this stability analysis based on our load case 1 here. And the number of lowest eigenvalues we're showing is 4. That's also by default. And everything else we really don't need to worry about. So we can hit calculate. And once the calculation is done running, you can see we have our results here. And we can take a look at our critical load factors for each of our eigenmodes. So our critical load factor for this first eigenmode is 135. And the critical load factor is the amount you would have to multiply basically your loads by in order to get an unstable system. Or it can be looked at as the total percent of the loads your structure can take. So it's very important to keep in mind if this number is under 1, then that means that your structure can't handle 100% of the loading that's applied to it. So I have only 100 pounds applied to this column. And let's say this number was under 1, then if it was 0.9, then my structure would only, or this column would only be able to handle 90 pounds, and anything exceeding that would cause an instability. So that's kind of the basic understanding of the critical load factor here. And then next thing we have is our effective lengths. And we can take a look at our effective lengths for our member here for each eigenvector. And we can also take a look at the critical load here. We can also view our results graphically and take a look at our eigenvectors. So if I go down here and click graphic, then we can turn our model around and you can now get a better look at the first buckling case or buckling form. And if I wanted to look at the other ones, we can go down here in the panel over here and look at and choose the tab filter, or no, factors, sorry. Under the tab factors here, you can take a look and you can see eigenvector number. Right now we're looking at 1, but we can change this to 2, 3, and then we can take a look at our fourth eigenmode. So you can notice that the weak axis of this column is in the y direction, about the local z-axis. So this is mostly the reason for this. That's why this column is deforming in this direction, because of the weak axes, and the moment of inertia in this direction the moment of inertia is smallest about the local z-axis. So if I double click on the column, we can take a look at the info about our cross section, and you can see that the moment of inertia about our z-axis, local z-axis, is 24 compared to 285. So this is the reason why the column is buckling about this axis. So now we can swap back. Let's swap back to RF stability. You can see we have it selected under our dropdown up here. So what I can do is just hit this button right here, RF stability. And then we can take a look again at our effective length factors. And I would just like to show you guys what it looks like when the structure is unstable. So we can go to our LC1 here and then double click on our loading. So if we increase this load from 100 pounds to something like 14 kips, we can click OK. And before we run our stability analysis, we already know that this structure is unstable. And if you have an unstable structure, you need to make sure that you are not running a second order analysis, because then our stability will not be able to show you the critical load factors. So we'll go back into our calculation parameters and turn this back into a linear analysis. And then we'll go back into RF stability. And we'll hit calculate. And once this is done, you should see we'll get a critical load factor below 1. So we have now a critical load factor of 0.966. So this factor being under 1 is telling us that our structure cannot take 100% of the 14 kips that we applied to it. So that's one way to, if you have a structure and you're getting an instability and you made sure everything's connected and everything looks modeled correctly, this is one way to tell if you need to maybe optimize some of your model. So with that said, I have another question for you guys. And if you could answer this, that'd be great. And then we'll go over the answers afterwards. All right, so the question was, or statement is, the critical load factor specifies which factor can be used to increase the load until the structural system fails. And it looks like everyone got it correct. So yeah, everyone had answered true. That was correct. Yeah, the critical load factor, if it's above 1, then that means your system or your structural system is stable. And if it's below 1, that means that it is unstable and the system will fail. So, and that all has to do with the loading basically. So great, we can go back to RFEM. And what we can do is now start creating our moment frame. So we're going to turn this column into a moment frame basically. And to do that, we can change our force here back to -5 kips. And we won't add any lateral loading. And then we can take this column and we can just make and highlight the whole thing, hold Control and select one of the nodes and make another copy 10 feet away. And then we can take or highlight these top nodes here. And if I change my work plane back to the XZ plane, I can just simply highlight both of the nodes here from left to right to only select the nodes. And then I can left click and just drag these down to about 10 feet. And now we have our columns for our frame. Now we want to create the beam for the top of our frame. So we'll go up to the create new member tool. And then the beam connecting these two is going to be, so we want to create a new cross section. And we want to go to W sections. And this beam is going to be an 8x15, so we'll scroll down. And we'll make it still a 992, so it's okay. Click OK. And then we can connect both of these columns. like so, with our beam. And now we have our moment frame. So what we can do is also, just to make this a little more interesting, we can add in a new member load. And this new member load is going to be -3 kip per feet. It's going to be a uniform force in the global z-axis direction. So we'll click OK, and then add in our loading there onto our top of our beam. And then we can run our calculation. So I'll just say calculate all. And then we can check out the internal forces and critical load factors. And now you can see we have our moments here along with our deformation. And then we can also, since we hit calculate all, we can just go to our stability and take a look at the stability analysis ran. So right now we're looking at our first eigenmode here, which is 4.89. So that's great, stable. And then we can scroll through and look at our other eigenmodes. So basically you can see that this frame here is bending out of plane, which is not ideal. And I can increase that by a factor, exaggerate that a little bit. So now we can see what the major issue is. If we had too high of a load, this is something we'd want to consider. So we can add in some supports here to keep this from bending out of plane. So if I hold Control and select both of the nodes here, and I can add in some nodal supports, create a new nodal support, and then change my degrees of freedom here to only support it in the Y direction, so to keep it in plane. So everything else, it can move up and down, left and right, it can rotate, but it just can't move in and out of the plane. So we'll click OK. And so now we have these supports up here at the corners. And if we rerun our calculation, we should see some better looking eigenmodes. And yep, so our first eigenmode or critical load factor increased from 4 to 21, so that's looking good. And we have no bending out of the plane for our frame here. And again, you can scroll through and take a look at the other modes. Also, you can take a look at the support reactions. Something else I didn't show. Yeah, so we have our support reactions here. So that's basically the moment frame. And so now we can move on and get into the next example, which is the timber truss girder. So this example will be basically just modeling this truss and then loading it, supporting it, and then I can show you how to design these members, and we'll be doing that based on the AWC standard. So let's hop into it. So what we're going to do is go up here to create a new model. And this one's going to be called timber truss girder. And I'm just going to add a number to the end of that. And then again, description. So the difference with this model is we're going to only model it as a 2D model in the XZ plane. And so this means that there will be no bending out of the plane, so no internal forces in and out of the plane. So we don't have to worry about that. And then we want to activate the combinations, set them to automatically. And for this, we're using wood. So we want to use the ASC 716 and the NDS. So that's just for this example, but you can also use other standards as well for wood. So again, we have the Euro code and also the Canadian code. And we'll click OK. And to start, we have, again, our blank grid here. You can see since this is only a 2D model, we can only keep our grid in the XZ plane. Can't move it in and out of the plane here. And there's plenty of ways that we could go about modeling this truss. We could draw our members manually and measure them out and everything. Or we can use a tool that RFEM has built in for creating truss systems. So if we go up here to tools, and then we go to generate model members, you can see we have a couple of options here for generating different models like 2D frames, tapered 2D frames. The tool we're interested in for modeling this truss is 2D truss. And you'll see once this tool opens up that we have a couple of different truss types here that we can choose from. We are just going to be focusing on this first truss type here. And then the next option is to choose your diagonals. So you can see these patterns here. We're going to be using this pattern right here with the double downward facing triangles here. And then the next thing we have is our parameters up here. So we can choose the number of bays, and the number of bays for this truss is going to be 10. And then the total length of our truss here is going to be 197 feet with a total height of 18.8 feet, and then a total side height of 8.53 feet. So that's we have the height, the length, and then the side height here. Next thing to define is the upper chord. So the cross-section of materials for the upper chord, lower chord, diagonals, and verticals. So this is pretty easy. All we have to do is create a new cross-section. And then we're going to import the parametric timber cross-section here. It's going to be rectangular. And this is for the upper chord. So we're going to make the dimensions of the upper chord 9 inches by 20 inches. And then we need to choose our material. So we'll go to, you can see I have my material already imported, but we can import material from material library. And you can see I have spruce softwoods, 15 or more lambs chosen. So I got there by going to the timber material and then sorting through the material category wood, North America, and the standard AWC, and then the latest NDS 2018. So I can choose my material, and then I can also see the material properties. So we'll click OK. And then we can click OK again. And what I want to do before exiting out of this box is I want to copy this cross-section description. So I'll hit Control-C and then hit OK. And now what I can do is I can do the same thing basically for the lower chord, but I'm going to create a new cross-section, and then I can simply just hit Control-V and copy that cross-section description into the box up here and change my material. And then I can simply, for this lower chord, I just want to change it from 9 by 20 inches to 9 by 22 inches, just to increase the depth, and hit OK again. And then for the diagonals, it is the same procedure, but for this one, we're going to change our dimensions from 9 to 8, and then, oh shoot, and then from 22 to 8. So our diagonals are going to be our squares. So they'll be 8 by 8, and we're going to change again this material. And then lastly, we'll create a new cross section for our verticals, and they're going to be a little different from our rectangular diagonals. So they'll be 8 by 4. And then change the material again. And so now we have all of our cross sections defined. We also have member types defined here. So for the upper and lower chord, we have beam type selected. And then you'll see for the diagonals and verticals, they are truss types. And the difference between a beam member type and a truss member type is that a beam has fully fixed connections in all 6 degrees of freedom. So then the translation and rotation is all fixed, so moments will be transferred between connections. But for a truss type, this is a pin connection, so rotation is allowed, so there will be no moments transferred between or through connections to other members for trusses. Next, now we can basically just click OK, and you can see that our truss has generated. So you can see all of our member types are created. One thing I do want to actually change is the verticals. We should probably actually increase the cross section of them. They are looking a little slim, so what we can do is simply just go to cross sections, and then we can double click on our 8 by 4 cross section here, and then we can simply just go up here and change this to a depth of 6, and then we should have an increased cross section there. And now the next thing we want to do is delete the bottom left and right members, because we're going to support our truss at the ends of the upper chords here. So what we can do is just hold Control and select these bottom left and bottom right hand members here and delete them. And then we want to delete the lines there as well. And the next important thing that we want to do is make our outer diagonal member beam types here, or outer diagonal members here beam types, because if we leave them as truss members, which they are right now, then there will be no bending moments transferred between the bottom and top chords. So I'm going to hold Control, select both of them, and double click on them. And then we can just go up here to member type and change that to beam. So this is a good visual. So if I have them set to truss, you can see the member hinge is grayed out, meaning that they're pin connections and we can't choose the member hinge for a truss member. But if I choose beam type, then you can see that the member hinges are available to be customized. So we'll click OK. And then we also want to make sure these members are included in our set of members. So a set of member in RFEM is basically multiple members all combined into a set of members. So if I change my rendering to wireframe, and zoom in, you can see my top chord here has a dotted line around all of the members up here. And this is showing you that these are all within a set of members. And basically what a set of members allows you to do is just to easily show the results for all of these beam segments as one large member. This just allows you to view the results easier. And it also allows you to apply loading easier, and also it allows you to run designs, or it allows you to design all of these members as one long continuous member. So you can see that the top chord has its own set, has a set of members, and then the bottom chord is also a set of members. But what we want to do is, you can see these diagonals are not part of the bottom chord set of members. So we can simply just double click on this dotted line here, and this will open up the edit set of members dialog box. So you can see this number, the second set of members lower is defined as the lower chord, and the members 12 through 19 are included in here, but we want to include the diagonals. So I can select them graphically and click OK, and then click OK again, and now you can see my diagonals are part of my bottom chord here. So now we can add in the supports for this truss. So we can go up here to new nodal support, and for the left side support, this is going to be a hinge support. So what we want to do is choose hinged, and you can see there's no rotation about the y-axis because this is just a 2D model. So I'll add in that hinge support on the left-hand side. And then for the right-hand side, we're going to add in a hinge support, but this one is going to be different. We're going to allow it to, so it's going to be a rolling support. It's going to be able to slide in the X direction. So we can release that. And so basically this one's only supporting the frame in the vertical direction. And also it can't move in and out of the plane. So we'll choose that corner, and then I can right click to exit out of that. Also, you can see my truss is basically outside of my grid here. And what we can do is have the grid automatically adjust to the size of our model. And to do that, we can go up here to the settings of work plane. And there's an option under here called dynamically. So for the number of grid points, we can have this set dynamically according to the size of model. So if we check that option and hit OK, now you can see our grid has automatically adjusted to the size of our model. Now I'm going to just change this back to a solid transparent display. And that's basically the whole modeling process done easily with the help of our modeling tool. So before we get into adding the loading and everything, I think now is a good time for questions before we take a break. So Amy, if there's any questions.
Yeah, we had a few questions. The first one is how to release moment between a surface and a beam. And I had already explained that this is with the use of a line release. So it might just be worthwhile to show somebody, you don't necessarily have to go through the whole process, but just where it is in the project navigator and how it could be applied.
Okay, yeah. Yeah, so if you have a beam framing in or attached to your surface on the edge there, and you want to release the moments between that beam, in the surface, like Amy said, you can use a line release. So if we went to the project navigator here and found line releases, you can see there's none in this model, but you could right click here and you could choose new line release. And so basically what you would do is choose the line which you're releasing graphically. And then you can see here, you can define the release. So like you said, you wanted to release the moments. You can go down here to rotational release and activate that. And then only the moments between that line and the surface would be released, or your beam. And then you would have to just choose or tell the program what surface that beam is being released from. And then that's basically it. So that's kind of the basics of how to use this line release tool to release the moments between a beam and a surface.
Yep. Okay, good. That should answer that question. The other question is how, let's say a user wants to only work with a particular story and they want to just activate that view. I think it's worthwhile showing the different visibility options and creating user-defined visibilities. Again, just a short example would be fine. And to preface this, again, we don't have the concept of stories, floors, or diaphragms in the program quite yet because this is a general FEA program, unlike ETABS, which is meant for building structures only. So that obviously has the concept of stories and floors, whereas something more like SAP 2000 is what RFEM is more comparable to. But with that said, it is possible to create these user-defined views that Alex will show you, that you can create your own story 1 view, story 2 view, and quickly switch back and forth to it.
Yeah, so you could just, if you had a story, I mean, I'm just going to use a couple of these members. So let's just say you have a building with multiple stories and you just wanted to switch to one of the stories and work on it. Let's just pretend that these 3 members here are a story. You could then hit the visibilities box here. And so I basically have these, my first story selected, and then I could choose this option here, create new user-defined view, and I could just name this like story 1 and hit OK. So now I can right click and I could even uncheck show hidden objects in the background. Oops. So maybe I did that wrong. What if?
I think you just didn't have the 3 members displayed when you created that visibility.
Oh, yeah, that might, okay, let's try that again. So turn off, oh. Yeah, so, or I guess the better way to do this would be visibility by window, and then we could select those members and then create a new visibility, and then that would be your story 1. And now you could turn off show hidden objects in the background. So that would be your story 1. So then every time you could create multiple stories, and then all you'd have to do is just go to your user-defined view and check on which story you would want to see. And then
Yeah, that's fine. I think that's the perfect way how to do it. And then the point being is that you can cancel out of this visibility. You can go back to the full structure, and you can always go back to this, activate this visibility story 1 that you just created, and it will bring you back to that original definition. So using those user-defined visibilities will be helpful.
Yep.
Okay, so we have a question about how to optimize members for design. I believe that you'll be covering this in the add-on module RF Timber AWC for this example, so we don't need to cover that now. Just maybe worthwhile to remember to show that, but I believe you already plan to do that.
Yep.
The final question, is it possible to create tapered members for the RFEM structure? So I think that's worthwhile showing the example. Again, no need to do it, but where you can set the member start and member end as different cross sections.
Yeah. Yeah. So yeah, to create a tapered cross section or a member, easiest way to show this is I'm just gonna edit one of these real quick. And that's kind of where the member end comes into play. So let's say you wanted to taper this member from the start, and you wanted it to start at 9 by 20 inches or whatever, and then you wanted it to go to, I don't know, 5 by 10 or something, you would just make the member end something smaller. Just example, if I change this to 8 by 8 and click OK, you can see that then the RFM will interpolate the start to the end, and then that's how you can taper your members like that.
Okay, I think that should wrap up the questions, so we can take our break.
Okay, great. Yeah. Yeah, we'll just take a 5-minute break and come back here at 3:10. All right, so the break is over and we can continue. So we got done modeling the truss before the break, and now we can add the loading in. So first thing we're gonna do is create a new load case by going up to this button, new load case. And again, action category is set to dead. You can see the self weight is activated with that -1 factor in the z-axis for gravity. And we're gonna keep that for this example. And we're gonna name this one self weight plus roof load. So we have our dead load case, and then we can go down here to this button, create new load case. And we can make the action category for this one snow. This is going to be a snow load. And this snow load is only going to be applied to the left side of our truss. Then we can create another one. This is going to be another snow load for the right side. And then we'll create a fourth load case. And this one will be wind on suction side, or actually going to make this wind uplift and change our action category to wind. So now we have all of our load cases created. I just want to show you guys the rest of these tabs. These are, the next tab is our actions tab, and you can see our multiple actions listed: dead, snow, and wind. And if I click on snow, you can see by default, snow is set to alternatively, which means the two snow loads will never be placed basically into the same load combination. And this means that I need to activate the option simultaneously, since both snow loads will be acting together on the left and right hand sides. You can then see in the next tab, combination expressions. We have our LRFD and ASD combination expressions. And if I click on this I button here called info about design situation, we can take a look at our design situation based on the code or whatever code you have selected. This will tell you what the design situation looks like along with the parameters. And then we can take a look at our action combinations. And also the next tab is our load combinations. And this is where basically multiple load cases are going to be combined into a larger load case, essentially with or without factors applied to them. So we have this base generated based on our design situation and the standard. So for example, this first combination is just 1.4 times our dead load. And so the last tab is our result combinations. And also, again, just to reiterate, load cases are calculated on a first order analysis, and the load combinations are all by default calculated based on a second order analysis. For the result combinations, these are envelope solutions and basically summarize the maximum and minimum results from all of the load combinations included in them. And so you can see we have, for this first result combination, all of our LRFD combinations or ultimate limit state design, and then we have our serviceability limit state or ASD combinations summed up or combined into this second result combination. And just some background, this combines the results. And so you could create result combinations without having to rerun results if you needed to. And now we have all of that defined. We can click OK. And we can now apply the loading to our structure. So right now we can go up here to the dropdown and we can go up to self weight. And then we can go up to the option new member load. And this will be the loading for our roof load. And what we want to do is change the reference to set of members. So we can just choose our set of members instead of having to choose each individual member here. And then the load type is going to be uniform. The distribution or load type will be force, and the load distribution will be uniform, and it's going to act in the global z direction. And this load is just going to be negative 0.2 kip per feet. And now we can just select the set of members once we click OK. And it's easier to, well, you can just, left click and select the set of members here. And now you can see our uniform load is applied to the true member length in the global z direction of our set of members there. Next is we need to apply our snow load on the left-hand side. So I can just hit this arrow, next load case, and then I can choose new member load again. And this is going to be a uniform force again, but this time it's going to be, instead of the true member length in the z direction, it's going to be the projected member length. And then we want to change our magnitude to 0.3, negative 0.3. And then we can click OK. And actually, we don't want to reference our set of members, we just want to reference members. And what we can do is just highlight this whole left-hand side. And I only selected the beams up in the upper chord. And you can see that it's the projected member length of that, taking into account how snow will act on our roof there. So we'll right click, and now we would just want to do the same thing for the left-hand side. So I'm just going to rotate my model, and then I can just highlight again, selecting only the beams up here, and then I can choose new member length. And then everything will stay the same. So pretty easy. And since we already selected the members before we went into the tool, if I click OK, we applied our load. Actually, I don't know why I applied it to the wrong load case. So Control Z is your friend, and you can go to the next load case, and then we can just redo that real quick. For our snow load on our right-hand side. There we go. Now we have our snow load for the right-hand side. And now all we need to do is add in the uplift. And so again, we're going to use the new member load tool. And the thing we need to change for this is the load direction. And we want this to be according to the local related true member length and the local z direction. So you can see that lowercase letter. And we're going to make this negative 0.35 or 35 pounds per foot. And we can click OK. Oh, we also need to change the reference to set of members, so we can select our upper chord. And then we can click OK. And now we have our wind uplift taken into account. So I'm going to run the calculation now. I'll click Calculate All. And while that's running, I would like to ask a question. And then we can go over the answer afterwards. All right, so the question was, which generate model tool can be used to most efficiently model a truss system? The options were continuous beam, 2D truss, tapered 2D frame, or 2D frame. And the best option is to use the 2D truss tool. This is the most efficient way to model a truss system with an RFEM instead of having to do it manually. So we can go back and take a look at our results that ran. And right now we're viewing the uplift load case, so you can see what our truss is doing when there's only uplift. We can change this display to show the cross sections in a colored display, so we can see those deformations a little easier. It looks like the max deformation for our uplift is 0.2 inches. There's three major steps when evaluating your structure's results. The first step I would recommend taking is to always take a closer look at your modeling to make sure that all of your members are connected to each other. This doesn't really apply too much for this model since we had RFM generated for us, but if you have a lot of members and maybe your results aren't matching up to what you expected, I would always recommend zooming in close to all of your connections here, because sometimes your connections may look from afar like they're connected, when in reality, maybe one of these lines is just slightly off from the node, causing a discrepancy. This mostly occurs, I would say, when importing a model from AutoCAD or from maybe Revit. Sometimes imports have unconnected members because difference in tolerances between the two programs. So always important to check that. Second step I recommend taking is to always check the deformations of your self-weight or dead load case. So if we go up to our self-weight load case and we show the results, right now we're looking at the global deformations, and you can see that our deformation is symmetrical, which is good. We have a symmetrical structure here. We can just look at the Z component. So this is something that you would want to double check if you have a symmetric structure, is if your deformations are symmetric. And our max deformation right now in the Z direction is 2 inches. So that's looking pretty good, as expected, I would say. And then the third check is to look at your internal forces. So again, if we activate members results, and then we take a look at our normal forces, you can see that our upper chord, we have compression forces for our normal forces, which makes sense in this layout. And then our bottom chord is blue, positive values, telling us that we have high tension forces basically, which also makes sense for this loading setup at the bottom here. So you can see in the middle, we have the highest tension forces of around 90 kips. And you can also take a look and see that we have something that, this is important to point out, is that you can see we have very high forces on our outside diagonal members here, which I did on purpose. So I can show you later how to optimize these, since these will be critical members, since their cross section is a lot smaller than the main cross sections that we created for our bottom chord here, and they don't really compare too much in size with the bottom chord and the tension forces that it's receiving. Next thing we can also take a look at are shear forces. These are pretty low since this is expected with a truss. Since we're working with a truss, we are not really expecting too high of shear forces. And then also our bending moments, we can see the same thing as shear. They're not too high, which is as expected since trusses mainly transfer forces, such as normal forces, such as tension and compression. We're not really too focused on bending moments. And now you can also check your support reactions. And on the left-hand side, this is another great way. I can also turn off the grid down here so we can see those values easier. But on the left-hand side, we're getting 31 kips. And on the right-hand side, we're also matching that number. So with a symmetrical structure like this, it's good to see both of those matching. That's what we would expect. And then in the last way to check your structure is to go down into the table down here, and we can take a look at table 4 results. And you can see for the self-weight plus the roof load that we can take a look at the sum of the loads in the z direction, and then the sum of support forces in the z direction. And you can see that both of those values match, so 62.18 kips and for our sum of loads, and then 62.18 kips for sum of support forces. So both of those should match because of statics and reactions to the loading. And you can see we're getting a deviation between those of 0%. So anything other than 0% deviation will be flagged by the program. So an error will be thrown up, and that just means that something is not correct with your model. So now we can move on to the design portion. And so I'm just going to change the viewing back to our internal forces. And like I mentioned before, whenever we're doing a material specific design in RFEM, we want to use the add-on modules. For this example, we can go up to add-on modules, and then we can go to design timber. And you can see we have multiple options. For this example, I'm just going to design it according to the AWC, but you can also see that we have the CSA for Canada. And then you can also use RF Timber Pro to design according to the Euro code. And again, you can find these add-on modules under the data tab in the project navigator, and they're listed here. So I could just go down here to, well, I saved RF Timber AWC in my favorites. To save something in your favorites folder for the add-on modules, you just need to right click on it and then hit favorite. And then you can see it'll move it to the top here. So that's an easy way to find them. So we can just double click on RF Timber AWC in the project navigator. And for this example, we want to, for this example, we want to start off by just designing the upper and lower chords, and then we can design the diagonals and then the verticals. So right now, we're in the RF Timber AWC add-on module. This is basically how the other add-on modules are going to look. It doesn't matter too much about which standard you're using. The layout and UI is all pretty cohesive. So we have our input data on the left-hand side here. So what you want to do is just first work down through this list here. So we'll start off in the general data. We need to tell the module which members we're designing. Right now it has the check here for all members to be designed. We want to uncheck that and delete the current list of members. because we just want to design all of our set of members. So now you can see how much easier it's going to be to only have to design 2 sets of members instead of a whole list of members. And then we just want to choose the latest standard, and we're going to be designing this according to our LRFD. And then once we have that selected, for our ultimate limit state design, we want to choose all of our LRFD or ultimate limit state combinations. So I can just choose the first one, hold shift, and choose the last one, and then just simply move those over using this arrow here. Now I could have just moved over the result combination for LRFD since this is an envelope for all of these, but having all of your combinations thrown into for design allows you to see which combinations are giving you issues and which ones are causing, which ones aren't passing maybe for your design ratio. Then what we can do is move on to the materials. And you can see we have our materials listed. So concrete you can see is red because we can't design concrete in the timber module. But you can see we have our spruce here chosen for all of our material or for all of our members. If we had multiple materials or used multiple materials, you would see those listed here. And then you can also see the material properties listed down below here for a quick look. Then you can also see our cross sections that we're using. So those are automatically imported, and you can see we have 4 of them. We have our 9x20, 9x22, and our other ones, and we can click on those. And then the optimization column here, I'll get into after we run our results, but keep that in mind that that's there. Then we have our load durations, and you can see these are automatically set based on the action that you choose for your load case. So you don't need to worry about that. So you can see here that the design situation or shortest load duration and a combination, or you can choose this and you can use user-defined settings. For now, we're just going to leave that as is and move on to the next category, which is in service condition. So you can see we can either choose between dry or wet conditions, and then we can also choose the temperature of which the structure will be placed in for either both of these sets of members. So we're going to leave that also as default as less than 100 degrees and also dry conditions. And then the next category we want to get into is the effective lengths. So for this, we're going to have to make some assumptions. So this is for your stability checks. So buckling about the x-axis or the strong axis, and then we have buckling about the weak axis or about the y-axis. And then we have lateral torsional buckling. And so the first assumption that we're going to make is that we're going to be having purlins connected to the top cord here, and all those purlins connected will be going out of plane. So we're going to assume that they're framing into the top cord here every couple of feet and that they are fixed to it. So what this means is that we do not need to consider buckling or LTB for our top cord here. So what we can do is uncheck buckling possible here, and we can uncheck the possibility for lateral torsional buckling. And then taking a look at our bottom cord here, you can see that we have no compression forces, only tension. That's what the positive values in the blue coloring is showing us. So without compression, we also do not need to consider the possibility for buckling or the possibility for lateral torsional buckling, so we can uncheck those. Another way of doing that would just be to go to the details option here, and then under stability, we could uncheck perform stability analysis. So either way works for that. And now we have all of our parameters. There's also some we have additional design parameters here. So right now by default, we're taking into account there's no shear reduction and we have edge bonding. So if you needed to change any of these, maybe you have no edge bonding and you have an odd number of lamps or an even number. And then if you want to take shear reduction into consideration, we also have that option. And then under cross-sectional area reduction, we don't need to worry about this either for this example. We'll leave that as is. And now we can run our calculation. And before we take a look at our results, I have another question. So a statement really, if you could answer true or false, and then we'll go over the correct answer. All right, so looks like most of you answered false. I see a couple trues. So the statement was a 2% deviation for the sum of loads in Z versus the sum of support forces in Z is sufficient, and that's false. So if you back to the idea of checking your model, if you see any deviation, if I go back to RFEM real quick, if you see any deviation when looking at your loading and the results, if you see any deviation between the loads in the Z direction and the sum of support forces in the Z, this deviation right here, if this is ever anything other than 0%, which most of the time it should be 0%, then that means there is something wrong with your model. RFM will give you an error if that ever happens, so you don't need to make sure you check this every time, but this is just a great way to know. But of course, that should make sense that if you have 62 kips of loading in the Z direction, you should see that equal reaction in your supports and the sum of your supports. So yeah. Now we can get back into checking out our results. From our design. So I now have my results here on the left-hand side, and you can see we can filter by load case, we can filter by cross-section, we can filter by just set of members. You can see when I'm filtering just by a set of members that our lower chord is failing, and I think you might be able to guess why. If we go to cross-section and we take a look at our cross-sections, they all look good. except for our 8x8 diagonals here, which are exceeding our design ratio of 1.0 for bending and tension. And this is kind of what we expected since we saw those high compression forces or tension forces. And this is a pretty small cross section. So we can go through details such as material data or characteristics. We can look at cross-section data here. We can also go through design and internal forces. So you can see here we're getting we have a normal force in this, and in our cross-section a max of 157 kips, and also some bending moment of 3 kip per feet. Then according to the AWC design, we can take a look at our adjustment factors, and we also very nicely have listed our references to the code here and where we reference the code to come up with these factors. So if you ever needed to double check any of these, always great to have those code references. So that's for tension stresses, and then our bending stress adjustment factors here. Then we have our design ratio. So this basically goes through and shows you the factors and parameters that go into coming up with the final design ratio. And again, we have some code checks down here, which equations we're using as well. So always good to know that. And now we can go through and I can show you how to go about optimizing this cross section. So the first thing we want to do is we don't really want to optimize this section for just meeting that 1.0 design ratio. So first we want to go to details and then other, and then we want to change this under other, our max allowable design ratio to 0.9, and we can click OK. It's going to delete our results, which is fine for now. And now we want to go to cross sections. And then we want to go to our rectangular cross section, our 8x8 diagonal here that was failing. And what we can do is under optimize, we want to click on the cell and then click on the arrow. And we want to set this to yes. And so then this box will come up and we can choose to optimize our base and height. So we'll choose base and height, and then we can choose this option down here, keep current side proportions. So the ratio between base and height, if we choose this option, will stay the same, which is nice. Minimum, we want to, well, minimum doesn't really matter since we're exceeding our design ratio. So we'll just set that to 8. Maximum, we'll set to just a whole number of 17. And then increments, we will set to 1 inches, 1 inch increments to increase or decrease by. Really, you can set this to what you prefer, but this works out here, so we can hit OK. And now all we need to do is hit calculate. And then you'll see that we are now meeting our max design ratio. So all of our cross sections here are passing. Our max design ratio now is 0.79 instead of above 1. We go to design by cross section and scroll down to our diagonals. Now they are a 10 by 10 or optimized to a 10 by 10. And the max for those is only 0.7. If we go to our cross sections, you can see that like I said, those diagonals were changed to 10 by 10. And you may notice that this cross section is blue instead of black like the other ones. This means when a section is optimized in a module, you can see it's nice because it shows you where the section came from. So you can see originally it was an 8x8, but now it's a 10x10. When it's blue like this, it means that only the optimized cross section is seen by the module or taken into account by the module. It's not actually, the module did not change the section back in RFEM. Back in RFEM, the section is still 8x8. So these results that you're seeing in the module are just based on it being 10x10. So what you need to do after you optimize your cross sections is you need to right click on the blue ones. And if you're happy with that optimization, you want to hit export cross section to RFEM. And if you have multiple cross sections you need to export, you can hit export all cross sections to RFEM. And it's asking, do you want to transfer them? If so, the results will be deleted. We'll hit yes. And then we can just hit recalculate, and the results will look the same, but now the cross section in RFEM is actually changed. So that's how you go about optimizing cross sections using the add-on module. So now what we can do is go up to File and Rename, and we can have multiple cases. So this case we'll just call the upper plus lower chords. And what we can do is create a new case, and we can design all of our diagonals. And we'll save our changes. And then what we want to do, again, is uncheck. We don't want to design all of our members. We just want to design the diagonals. So what we can do is hit this button to select them graphically. And an easy way of selecting all of them graphically instead of clicking all of them is I want to just show you this tool up here called Select Special. And this is handy if you have a large model and you need to select all of the same cross section within a model. You can hit this activate members. Well, we go down to members and we hit activate, and then we have options over here on which members we want to select. So we can select ones with cross sections, and we can choose, okay, we only want to select our 10x10s. And yeah, and click OK. And so since we exported all of our optimized cross sections, they're all optimized. And so we probably should be seeing some green lights for all of them, or green smiley faces. So what we can do is select all of them, move over our combinations, and then choose design according to, go through our materials, cross sections look good, load durations, and service conditions will leave the same. And then for the effective lengths for all of these diagonals, this is where we would leave all of them as the full member length, since they will all be experiencing, or might be experiencing, or it could be possible that there's buckling or lateral torsional buckling going on. And then also, again, additional design parameters will leave the same. And so then we can run our calculation. And now you can see that we have our max design ratio of 0.82. So if you're curious which one is which combination is causing the highest design ratio, we can filter over here to max and hit apply filter. And now you can see that bending and tension is what's causing, and from combination 6 here and member 30 is causing our highest design ratio. So good to know. And if I can click on the member here, and this red arrow is showing me which member is giving us the highest design ratio, or our critical member, basically. And then we can also take a look at our results graphically if we wanted. So we can hit graphics, and we can see also graphically our design ratios as diagrams on each of our members here. So these diagonals in the center here are at least, we don't have to worry about those at all. We could, if we wanted to, increase those or decrease those cross sections. And yeah, and we can go back. And then we can create a new case and design our verticals. And again, uncheck all graphically and use our select special tool here. Actually, I forgot to, oh no, I lost my window. Well, so yeah, so I lost my select member window, and not sure what happened to that. So let's see if we save. And we'll just save all. Well, it looks like we have some time left. It looks like we about have 5 minutes left, and so the last thing I was going to do was just design these verticals. Is there any questions that we could go over before we conclude today's training, Amy?
The only question that came in was the ability to analyze shotcrete. And I had answered in the chat, but just to clarify this, that realistically, if there doesn't exist a material in the program, you can always add a user-defined material. So as long as you have those properties and you can essentially copy the existing concrete material and add in the shotcrete material properties, then the full analysis can be completed. I don't know about the specific standard that you're referring to for concrete design and if it addresses a material like this. I know the ACI standard and CSA standard for North America, I don't believe address this. So the design modules are based on just typical concrete materials, which are also listed within the program. But again, it's always possible to analyze any material within RFEM as long as you have the relevant material properties. I think that is really the only question that came in for now. Maybe a few more will filter in before we wrap up today's presentation.
Mm-hmm. Yeah. Yeah, if anybody has any questions, feel free to ask them, as right now is basically just like an open discussion for the last 5 minutes. And we can go over any topics that you would like to ask about. That's while you're typing, maybe I'll just go over the last couple slides. So we have free online services on our website that are handy. So we have our GeoZone tool, cross-section properties. You can check out our, definitely recommend checking out our FAQ and knowledge base section of our website for questions. Definitely FAQs. We upload a lot of them, and they're very helpful and lots of common questions that people have. Knowledge base articles, great for specifically designing certain structures according to standards and things like that. Our models to download section, we have some interesting models that have been uploaded from customer projects and also by us. So always a nice way to, maybe if you're looking at a more complicated structure, you can download something similar to that under the models to download and get an idea of how to maybe model it. Free online services, we have our YouTube channel that includes webinars given by Amy that are very helpful, videos uploaded by me, so specifically student videos. If you're first using RFEM, some introduction videos, those are always very helpful. Like I said, we have our e-learning videos for students. You can download and find free student licenses on our website. So you can work with an RFEM for free if you're a student and you have access to all of the add-on modules. All you need to do is just show a proof of enrollment. And probably our best service is our free support via email. And I highly recommend taking advantage of that. If you're stuck on something, if you have an instability that you can't figure out, you can send your model to us and we can answer your questions or take a look at that. So is there any questions that anyone answered or asked?
There are a couple coming in. The first one is there ability for nonlinear dynamic analysis?
So no, we don't do, I'm pretty sure we don't do.
The add-on module extension RF Dynam Pro nonlinear time history will
Oh, yeah.
allow for the nonlinearities to be considered for time history analysis. This is a module extension, so you have to have the Dynam Pro force vibrations module. So yes,
Oh,
that
that's right.
is possible. Software for foundation design, we do have an add-on module for foundation design according to the Eulero code. This does not include the standards for North America, but you can find more information on our website about bucket foundations, for example. If you're designing just a slab on grade or grade beams, the general concrete add-on modules can be used, which do include the North American standards. Someone asked about a seismic design course. So we do offer this, but these are paid trainings. So seismic design according to Eulero code, and possibly one according to the ASCE 7 or NBC standard. They are 3-hour trainings, but they do cost money, even if you're a student. So if you're interested with that, you can find that under our events page. Otherwise, we have plenty of free webinars on seismic analysis and design on our YouTube channel. The final question, Arwin simulation in RFEM. Alex, maybe you just want to explain what Arwin simulation, you don't need to show an example, but just give a brief explanation.
Yeah. So with Arwin simulation, you can take basically any structure from RFEM and import it into a simulated wind tunnel using Arwin simulation, and you can run it through a numeric wind tunnel and get those pressures and convert those pressures from the simulation into loading forces and import those back into RFEM, and then you can have your wind load cases basically generated based on the results from our wind simulation. So that's kind of the overall gist of our wind simulation.
Yeah. And we have additional webinars on our YouTube channel where we show an example of this whole workflow from RFEM into our wind simulation and then exporting those loads back into RFEM. So again, refer to our YouTube channel for this. I think the only other thing to mention is that, again, the certificate, the PowerPoint, the recording, the models, these will all be sent to you, to all attendees today within the next 1 to 2 days. It does take us a little while to kind of gather all this information. So keep an eye out for that. And that would be it from my side.
Yeah, awesome. Thanks for the great questions, and thanks everyone for attending. Yeah, hope everyone has a great and safe rest of their week, and look out for that recording and have a good one. Thank you.